Good evening. Welcome to Krishna's classroom. Tonight we take up the concept of connectedness. Intuitively, a metric space is connected if it's a single piece. So we should just note it. Intuitive meaning is that a single piece. Now let us give some examples. For instance, R with the usual metric is connected. We cannot define what it is, but it's in single piece, therefore it's connected. Whereas if you look at this one, R/0, which is essentially minus infinity to 0 that means 0 is deleted from it, is not connected because it is broken at somewhere in the middle and 0 does not belong. Okay, so it's in two pieces actually. Now other examples are an ellipse or parabola in R2 are connected. Whereas a hyperbola is not connected. Because it is not in one piece. We remove a single point it is still connected. Whereas if we remove the unit circle, then it is not connected. I think we have considered enough examples. More sophisticated examples we shall look at later. So let us start defining this mathematically. Before that, we shall work in a metric space. So let metric space. Now we define the following. Definition. Two sets A and B in X are separated this is the terminology. Separated if both A intersection B bar and A closure intersection B. That means the limit points of B do not belong to, that is, the limit points do not belong to A, and the limit points of A do not belong to If that is the case, then we say that these two sets are separated or not connected. Okay, they are separated sets. Now let us examine this point. Here you see that the interval minus infinity to plus infinity minus infinity plus infinity, 0 and are separate. And if you take the case of the hyperbola, then you see that the two branches that you have are separated. Okay, you take x square plus square minus y square equal to 1, and they are separate. So that's these are the examples that you can immediately see. But this is the abstract definition that A and B are subsets of X, and we have intersection of A with B closure, which in turn tells that if you take all the limit points of B, this no limit point of B is in A, no limit point of A is in. That is the meaning of what is called, or that is what you mean by the two sets are separated. So let us now remark. Now separated sets are disjoint. But disjoint sets need not be separated. For instance, suppose you take, for instance, for example, the set minus infinity to 0 and 0 to infinity are disjoint, but not separate. The reason being that if you take this as A and this as B, then when you take B closure, 0 comes into the picture, and you take the intersection of these two, then of course that is not empty. So here A equal to, define A to be minus infinity and B defined as 0 infinity, then A intersection empty. But A intersection B closure consists of the singleton point 0, which is non-empty. Although A closure intersection B. So one of the conditions failed. Therefore, they are not separated, but they are disjoint. Okay. Now we define connectedness. A set E contained in X is said to be said to be connected if E is not a union of two non-empty see if E can be written as the union of two separated sets, then it is not connected. So it's a negation of that, what you call connectedness. We say that E is connected if it cannot be written as the union of two non-empty separated sets. Okay, so let us. So that's a central definition of connectedness. So there are many equivalent forms of it, which we shall explore in due course. Now the connected we shall explore the structure of connected subsets of so we are specializing in R. R is taken as the metric space in which we are now exploring what connectedness means. In R, connected structure. So we have the following theorem which gives this structure. So we have the following theorem. A subset is connected if and only if it has the following. namely x belonging to E, y belonging to E, and x that means any intermediate point of 2 points x and y in E should also be okay. Now you can easily see that this is violated here. So suppose you take 2 points say -1 and 1, then you see that in the space, see if E is equal to, if E is then for -1 and +1, we have -1 less than 0 less than 1, and 0 does not. So that's an example. So in R, there is an alternate way of identifying what are called connected subsets. Now let us look at the proof of this theorem. So you take x to be equal to R. We are working in R. And E is contained in R. Some subset. Suppose x belongs to E and y belongs to E. are two distinct points. Then, and let us assume that without loss of generality, then there exists a Z belonging to the interval, the open interval xy, such that this is the assumption that we have to. So rather we will write it this way. Let Z belong to xy such that Z belong. Z does not belong. So this is the assumption that we are making. Now we want to show that. So this is the supposition. Okay. So this is the assumption that we are making, and we claim that E is not connected. So what do we have to do? We have to produce two separated sets A and B such that E is the union of A and B. That is, we have to show that there exists A, B non-empty subsets of E separated such that E equal to A union. This is what we should do. So we have to do the construction work. Essentially, we have to find out the construction, do the construction. Let us now construct the subsets A and B which are separated. Non-empty separated subsets A and B of. Okay. Let AZ defined as E intersection and BZ defined as intersection when X belongs to AZ and Y belongs to BZ implies AZ and non-empty. Further, you have E equal to PZ. Now, AZ is contained in minus infinity and BZ infinity. Now it is easy to see that further AZ closure intersection BZ is empty and AZ intersection BZ closure, that is AZ and BZ separated. Therefore, we have successfully written E as a union of two non-empty separated sets. Okay. Therefore, which implies E is not connected. Now this implies so what we have proved is that is the following. So what we have proved is this. Suppose we have two statements here. The first statement is that E is connected. Second statement is that given and these are the two statements of the theorem. So what we are asserting is that A implies B and B implies A. What we have assumed is that, so instead of, we wanted to prove A implies B, and this we know is equivalent to not B implies not B. This is exactly what we have done. We have assumed, we have assumed that B does not hold. Then we proved that A is not satisfied. That was our strategy. Okay, so this is what we have done up to now. Now we take up the converse. What is the converse? So we have not B implies not A, that is so we have proved A implies B. Now the converse is this, that B implies B. So B implies A, again we use this contrapositive one. What do? We assume, see, B implies A if not A implies not B. Okay. So we assume that is, this is equivalent to not A. That is the strategy that we are going to. So we are going to prove that not A implies That is how we are going to work on this. So let us assume. So not A means E is not connected. E is not connected. Then there exists A contained in B contained in B, A comma B non-empty, and A and E are separated such that E equal to that is the meaning of not A. Okay, so let us start with the assumption. So there exists are separated and A union B, that is the assumption. What we claim is that for X belonging to A and Y belonging to B with X less than Y, there exists Z such that X less than Z less than Y and does not belong. That's what we want to do. So this is the claim. So let us do this. So I suppose the strategy is very clear. So once we prove that, it would mean that E is not connected. Sorry. Yeah, there is a Z that lies between X and Y for each X and Y, X belonging to A and Y belonging to So pick it is possible because both A and B are non-empty. Non-empty. Now, without loss of generality, assume x less than. Now we have to identify a z. We have to identify a z which is not in A as well as not in B. That's what we have to. Okay. So how to identify this? Let us give some example. For instance, let us explore it. Consider E to be equal to. Then E is not connected. This is our visual feeling. Where does the disconnection occur? The disconnection occurs what? Okay. Now we have to, let us pick an x belonging to and y belonging to 100. Two elements. I mean, you can actually give some. Okay. Now you see that you have to arrive at this 1, but how do you get hold of this 1? Okay. So what one does is the structure of E need not be this elegant. Okay. Now what we can do is the following. Okay. You take this one. Consider x comma y. That means, see, we are looking at this one. 1, 2. This is what we are looking at. So x is some element here, y is some element. Now we have to converge on this particular one. But how to get that? Okay. So we know that say A and B are there. What is A and B? Okay. So you take this one. A is in this case 0, 1 and B is in this case 1, 2. Okay. So how do you get hold of this one? So this is your E. So you take E intersection A or rather the particular x, y. Okay. So xy is this particular term. Now, see, the point is that in a specific situation there may be more than one point where there is a breaking difference. So what one does is you take the supremum of supremum of E intersection the closed bounded interval xy. So that in this case is equal to 1. So that seems to be the path. So we are exploring this example. And now let us work this strategy. Supremum of a closed bounded interval xy. So this is the definition of Z. Now what we assert is that Z has the required property. What are the properties? Okay. So let us work out this. Now what can you say about Z? See, observe that Z belongs to A. Z may be in A or may not be in A, but it's certainly in A closure. So keep this example in your mind, then the proof would be clear. So one is here in the closure of the interval 0, 1, open interval 0. That is the corresponding statement here. Now A intersection empty. That's how A and B are chosen. Therefore, that implies Z does not belong to B. In particular, what you can say is that X less than or equal to we have picked up some X. So the X that we have chosen happens to be 1. That is the situation that we are taking, or equal to. Now if Z does not belong to A, then it follows that X is less than Z that is Z does not belong to. Why it is so? The reason is this: since Z does not belong to A and we have earlier proved that Z does not belong to. Okay? Z does not belong to. So Z does not belong to A, then you have these two conditions, and therefore Z does not belong, because E is the union of that is the reason. Now that is the situation where we have assumed that Z does not belong to. So suppose Z belongs to you. Suppose Z is in A. Now the case that we have considered is Z is equal to 1. Okay? That is Z does not belong to. And that Z cannot be in B. Okay? So what we have asserted is that Z is not in A, Z is not in B. In B, therefore Z is not in there. Now suppose Z belongs to A. Then B closure. Hence, there exists Z1 such that less than Y. Okay. So Z is not in B closure. Then there exists a Z1 such that Z1 lies between Z and Y. Then we have, what we have is X less than Z1 less than Y and we observe that Z1 cannot be in A. Why Z1 cannot be in A? See, that Z1, why it is so? Let us, if Z1 belongs to A, then Z is less than Z1. And what is Z? The definition of Z is the supremum of A intersection the interval, the closed interval xy. Okay. And this violates, if Z1 is in A, then it would violate supremum of in fact Z1 is bigger than Z, therefore, and it is also in A, therefore this, therefore Thus again, so that completes the proof of A union B. That is, there exists Z lying between X and Y, such that that is the proof. Okay. One of the consequence of this is that a consequence of, say, corollary, all intervals because you see that the basic property of an interval is that if AB is an interval, then for any x comma y belonging to AB, x less than z less than y implies z belongs to A. That is the basic property of the interval. And you see that this is a characterization of intervals as well. So all intervals are connected. Okay. So I think we'll conclude this talk here. Continue with it possibly tomorrow or day. Thank you very much.